Hello everyone. In this part of video, we are going to see the ShiftMate Phase 2 navigation function, engineering knowledge, numerical topics. You have in your exam paper one numerical question which is compulsory and it carries 25 marks. There are three types of numericals. Any one you may get. One is the diesel engine power calculation. The other type is from propeller pitch RPM. You have to find the ship speed. Then ship speed and fuel consumption type. So out of these three, you may get any one, and it is also a compulsory question. So in this part of video, we will see how to calculate engine power. Mostly all ships, the propulsion engines are two-stroke, slow speed, crossway type, heavy oil fired, directly reversible engines. So what is the advantage in this? The engine speed is low. The propeller efficiency is maximum when it runs at a very lower RPM. And also when the engine speed is low, the cycle time is more. So you have more time available for burning fuel oil. This one. So you can use cheaper fuel. And since it is directly reversible, it is an added advantage. This one. Now let us see the units first. The force is always mentioned in Newton. The force is in Newton or kilonewton or meganewton also. But Newton is the basic unit. Similarly, work done, it is Newton meter. Force into distance is Newton meter. Power is rate of doing work. So it is watt. Generally, watt is being the smallest one. So we always use either kilowatt or megawatt. So usually the engine power is in terms of kilowatt. The small IP, this is the power developed in the engine cylinder. The power developed in the engine cylinder. So when you put this capital I, it is the power developed in the engine. So you will have to multiply by number of cylinders from the power developed in one cylinder. The power available at the flywheel, this is generally known as brake power. This is after compensating the friction losses in the engine drives and other friction losses. So this is the brake power. The ratio between the brake power and the indicated power of the engine, this is the mechanical efficiency. So this may be around 88%. Now the power available on the shaft, it will be almost the same like brake power. But if you have a shaft-driven generator, then you may have to deduct that power and the remaining only goes for shaft. So this is the shaft generator power. So SP is BP minus SG. Otherwise, both are same. The power delivered to the propeller. This is after meeting the transmission losses. Here you have steady bearings and here you have stuntive bearings. So they all absorb some power. So the power delivered to the propeller, that is the delivered power divided by the brake power or shaft power. This is the efficiency of transmission. Say this will be around 97%. So about 3% losses we can account for. Now the power delivered to the propeller converts that into thrust power. So thrust power divided by the delivered power, this is the propeller efficiency. The propeller losses are more. So the propeller efficiency, we can account it as 70%. So what is given to the propeller, only 70% we get as output. The hull is moved with this power, that is the effective power with which the hull is pushed. So directly we can get from the delivered power, this is EP by dP, this ratio, this is called quasi-propulsive coefficient, which is inclusive of this hull efficiency, propeller efficiency. So propeller efficiency and hull efficiency put together, it is called quasi-propulsive coefficient. So this may be accounted for about 65%, 65 or 67%. So this is the basics of this power. Now this is the indicator gear. This gear is connected to cylinder head indicator valve, and when the valve is opened, the cylinder pressure has communication gear. So depending on the variations, this pointer also moves. Here we are attaching a paper, which is the indicator paper, and this stylus can scribe on that, and this drum is rotated by this cord, which is connected to a cam. This one. So this is how the diagram is traced in this. This is the pressure axis, and this is the volume axis. This is the BDC and this is the TDC point. And from here, let us imagine a horizontal piston. As the piston starts moving upwards, the pressure inside the cylinder, it is compressing the air, so it is increasing. And at some point here, the fuel is injected and the fuel starts burning and the expanding gases push the piston down. So this is the work done. Here the work is done on the piston. And when it comes to somewhere here, the exhaust valve opens and the pressure is reduced in the cylinder. So this is, it goes to, this is the BDC position. So this is the diagram. This diagram represents the work done inside the cylinder. This P into V is work done. This is work done. That is kilonewton per meter square is the pressure and volume is in meter cube. So kilonewton meter, this is the work done. How many times this work is done in 1 second? That is the power realized in the cylinder. Now the total work done inside the cylinder is this entire area represents the total work done in the cylinder. Out of which we take back some work for compressing the air charge, all those things. So this is the negative work. So this is the negative work. It means the area of the cord, that is the net positive work we obtained from burning fuel. So this is the net positive work. This is the net positive work. Now you can see the pressure is not same at every point. The pressure is minimum. As the piston is approaching TDC, the pressure is rising, and after burning the fuel, once the fuel injection starts and the pressure is rising and the burning fuel now pushes the piston down, so the volume is increasing and pressure is reducing. So pressure is not same throughout. So for our calculation purpose, we must assume that a constant pressure is acting right from TDC to BDC, and that is acting on one area, that is the force. The force acting on the piston is moving the piston from TDC to BDC. So that is the distance it travels, which is the work done. How many times this work is done in 1 second? That is called power. So we want to find the power now. First, what we have to do, we must find the mean pressure of all these variations. So for this mean pressure, how we can find it? This is the pressure axis, and we first find the area of this diagram. So there is an instrument called planimeter, or nowadays the computer system can directly give you the average pressure. So this mean pressure for calculating, first we find the area of the diagram. The area of the diagram, if you divide it by the length of this diagram, length means from TDC to BDC, that is where the piston travels. So this is the length of the diagram. So if you divide this, you get the average height of the diagram. Average height of diagram. Usually this will be given in millimeter square. In the numerical, they will give in millimeter square, and length of the diagram will be in millimeter. So the average height of the diagram you will get in millimeter. The spring, what we use to measure in terms of this pressure, so that is giving in terms of this millimeter here. So the spring scale, that is 1 mm equal to, what is the pressure it is given? Let us say it is 1 bar. 1 mm represents 1 bar. So if you get the average height of the diagram, let us say 15 millimeter, it means the mean effective pressure is 15 bar. So now by doing a numerical, we will see how we have to have this approach. Now, this is the uh, problem. Area of this, suppose this is related to four-stroke engine. Area of the indicated diagram is given. It is taken from one cylinder. There are 6 cylinders in the engine and they have given the particulars for one cylinder. And it is also a four-stroke engine. See, these things, they have significance. So you should read it carefully, all these things. Area of the indicated diagram is given as 500 square millimeter. Length of the diagram is given 100 millimeter. So from this, you can find the average height. That is 5 millimeter will be the average height. The indicator spring constant, spring scale is given. Each millimeter represents 2 bar. The diameter of the cylinder is given, that is 300 millimeter, and stroke length, that is TDC to BDC or BDC to TDC, both same. It is 620 millimeter. RPM is given. See, since it is 4-stroke, you must know that every 2 revolutions will have only 1 power stroke. So when there are 10 revolutions in 1 second, in 1 second, you will have only 5 power strokes in that cylinder. So that is very important to know. Now we will do this. This is a 4-stroke engine and this is having 6 cylinders. Area of the cord is given as 500 millimeter square and the length of the cord, this is given 100 mm. So area by length, this gives the average height of the cord, which is 5 mm. This is the average height of the cord. Now each mm, it represents 2 bar. So 5 mm represents 10 bar. Now what is the formula for finding the indicated power in the engine cylinder? This one. Now whether it is 2-stroke or 4-stroke, now this is the indicated power per cylinder. This is equal to the mean indicated pressure into the stroke length into the area of the cylinder into number of power strokes per second. N is, if you keep it like number of power strokes per second, you will not have confusion. Here, we have to take care of the units first. Usually the power is mentioned in kilowatt and the mean indicated pressure, this should be in kilonewton per meter square. This one. And this will be in meter, stroke length. And area of the cylinder will be in meter square. This one. And the number of power strokes, that is per second. This one. So they get cancelled. Kilonewton meter. Newton meter is joule. So kilojoule, joule per second. So this is also kilowatt. So when you want to have kilowatt, you must convert this pressure into kilonewton per meter square and you are not supposed to use it in bar. That is very, very important. In whichever unit you measure the pressure, you have to convert it into kilonewton per meter square. Say 1 bar is how much? 1 bar is 10 power 5 Pascal, that is Newton per meter square. So you can write as 10 power 3 into 10 power 2 Newton per meter square. Since we are getting here kilonewton per meter square, so this goes off. So this will be kilonewton. So 1 bar is 100 kilonewton per meter square. 1 bar is 100 kilonewton per meter square. So what we have to do here, now IP equal to, you can write this one. So IP equal to mean pressure. This is 10 bar. 1 bar is 100. So 10 into 100. So this is so many kilonewton per meter square into stroke length. Stroke length as given in the problem, it is 620 millimeter. So 0.62 into area of the cylinder, that is 5 by 4 into d square, diameter of the cylinder given as 300 millimeter. So 0.3 meter, 0.3 meter d square. And RPM, here it is given revolutions per second is 10. But say in 1 second, 10 revolutions. But in in 4 stroke, every 2 revolutions will have 1 power stroke. So it means number of power strokes will be 10 by 2. So that is 10 by 2. So if you solve this, you will get 219 kilowatt. Now for the whole engine, if you calculate, it will be 219 into 6 cylinders are there, multiplied by 6. So many kilowatt. This is the engine. So this is for 4-stroke engine. So what is important in 4-stroke engine is, this is 6-cylinder, 4-stroke, area divided by length. You find out the average height, multiply by the spring constant, convert it into kilonewton per meter square. Then you can remember it as plan, indicated power per cylinder, that is plan. This is the pressure, length, stroke length and area of the cylinder into number of power strokes per second. Finally, if it is asked for the whole engine, then multiply by number of cylinders. So it means what assumption we make, all cylinders are developing equal power. Now let us see the for 2-stroke cycle engine. Now in the 2-stroke, the area of the indicated diagram taken, a 6-cylinder engine, 2-stroke, that is 450 millimeter square, length of the cord is 72 millimeter. And spring scale is given, 1 mm represents 1.5 bar. Diameter is given, stroke length is given, the speed is given. So what is the significance in this? Speed is 105 RPM. It means in 1 second, 105 divided by 60. Each revolution will give you a power stroke. So whatever you get RPS, that is the same number of power strokes. So how to solve this problem now? Then state the assumption made. The assumption is when you calculate power for one cylinder, now for the whole engine you are multiplying by 6. It means each cylinder, all cylinders develop equal power. So that is the assumption you are making. Then mechanical efficiency is given, transmission losses given, and propeller efficiency is given. You are asked to calculate thrust power. So we see this problem now. Area of the diagram, it is given as 450 millimeter square. Then length of the diagram given as 72 millimeter. So average height of the diagram is 6.25 millimeter. And each millimeter represents 1.5 bar. So 6.25 millimeter, it represents 9.375 bar. So which can be mentioned as 937.5 kilonewton per meter square. Now indicated power for the engine is, for the cylinder, this is, we have seen plan. This is 937.5 kilonewton per meter square. Stroke length. Stroke length is 1800 millimeter, so 1.8 meter. Area of the cylinder. Diameter of the cylinder is 900 mm given, so it is 5 by 4 into 0.9 into 0.9. Listen. 5 by 4 d square. Listen. Then last is number of power strokes per second. Listen. The RPM given here, it is 105. Listen. So 105 by 60 will be per second. Listen. And every revolution there is one power stroke. So if this cylinder is going to get every revolution one power stroke, so 105 by 60 will be the value of M. So if you calculate this, you get the indicated power in one cylinder will be 1878 kilowatt. And there are 6 cylinders, so indicated power of the engine is 1878 into 6, which will be 11,266 kilowatt. Now we have the indicated power for the engine. This one. This is the indicated power for the engine. This one. Now this is the brake power. And this is the power delivered to the propeller. And this is the thrust power which the propeller converts it. This one. So first they have given the mechanical efficiency as 90%. This is 90%. And the transmission efficiency is given as 97%. And the propeller efficiency is given as 65%. So we know IP, we know mechanical efficiency, so we can find out the brake power. The brake power is, indicated power is 11,266 kilowatt multiplied by mechanical efficiency 90%. So multiply by 0.9, that is 90 by 100, that is 0.9. So this is 10,139.4 kilowatt brake power. Now What 10,139.4 kilowatt you give here, only 97% of that it reaches here. So the delivered power will be 10,139.4 into 0.97. So that will be the power delivered to the propeller, which will be 9,835.2 kilowatt. Now, out of which the propeller is able to convert into thrust power only 65% of that. So thrust power is 9,835.2 into 0.65, which will be 6,392.89 kilowatt. So this is the thrust power what we get from the propeller. So these two problems, just if you can understand clearly that how to apply this formula, that is how to find the mean effective pressure, then all this and take care of the units, you will not have any difficulty in doing this. Yes. And also you have to remember this, the power flow. Power developed in the engine is indicated power. Available at the flywheel after meeting the engine losses is brake power. After meeting the shaft losses, given here is delivered power. The propeller takes that delivered power and converts into thrust power. Yes. Suppose they have not given any transmission losses. All you need to do is you can safely take the brake power and power delivered to propeller. Both are same. But it is better to write in the exam within bracket ignoring shaft losses. So this what we have seen in this, how to calculate engine power and how we arrive at the various things in this. So this is all about calculation of engine power. And all you need to know is how to apply it, that is in terms of that power strokes. For two stroke, how to apply, and for four stroke, how to apply. This is very important. Yes.